All right, so we're going to talk about area of polar curves now. Area of polar curves. So we're still in Unit 2, but we're on the last section. Area is the last thing we do. So area of polar curves. So I can find the area of a polar equation. So we want the area inside the shape of the polar curve. All right, so area in a polar curve. The important thing to remember, just with the parametrics, is the curve can only be traced out once on your interval, because if it traces out twice, then you're going to have twice the amount of area. All right, so that makes it kind of tricky. So you got to make sure that when you are doing the area, that you only trace out the curve once. Now, we're going to spend a couple days on this because this is kind of interesting to think about how these curves are created and how area is going to work. So it's going to take a couple of days to do this, and I've got several activities for us to do. All right, so we're just going to start simplistically today. All right, so R is some function. So to find the area of this polar curve R, we're going to do the integral from A to B of 1/2 R squared d theta. All right, so I think of this, you've got some polar curve here, and you're going from, I think of it like a lighthouse. Think of the lighthouse at the pole here, shining its light, and as it turns, it goes this way. As it turns, it shines the light out. All right, so if I'm wanting the area of this curve from, say, pi over 6 over here to 3 pi over 4, then my integral is going to be pi over 6 to 3 pi over 4, and it's just going to be 1/2, and then the function for this cardioid here squared. All right, so that is how you calculate the area, and that would just give us the area of just this part. As it goes from pi over 6 over to here, it would be the area traced. And remember, R is the length from the pole out. All right, that's what R is. So it's adding up these little teeny semicircles, I guess, or little teeny segments, 1/2 R squared as it rotates around, okay? So what about the area between two polar curves? All right, what about between them? Okay, so between polar curves, it's going to be just like when we did discs and washers last time. You've got to do the outer function minus the inner function, okay? So in this picture here, I just made an example by using two simple circles just to kind of explain it. Again, you can only be traced once on the curve, on the interval, whatever the interval is from A to B. We're going to have two functions, a big R and a little r. My big R is my outside function further from the pole, and then my little r is the one closest. All right, so you're going to do your distance out minus the distance on the inside. So it's this length minus this length, which would give us this little length in here. All right, and these are little wedges, like little, it's how you get the, it's because we're circular, so it's like doing 1/2 pi R squared. So that's what we're doing. It's just little wedges. All right, so to figure out the area of just the pink one, I want the big radius minus the little radius, and that'll give me the difference here where it's pink. So that's why the equation is 1/2 big R squared minus little r squared. And so here in the actual example I drew, we're going from, this would be pi over 6 around to over here to pi over 3. That's what these two lines are here that are on here. So, and then it would be 1/2 the big R squared. So the big R squared would be the circle that's 3 because it's on the third ring from the pole. And then minus little r squared, so this is big R, and then little r would be 2 because he's on the second ring from the pole. So it would be the furthest out function minus the closest function. And the easiest way to do that, I usually just draw an axis to see who gets hit first and then who hits second, to see who's the closest and the furthest away. All right, and that's all this is. So it's kind of like the washer method. Now, we also will sometimes need to find the intersections. So on this problem I gave you over here, I had the intersections that we were going to go from pi over 6 to 2 pi over 3, because especially since that's what's written on the integral right there. But I had that already done. So what if I have two polar curves and I don't know their their limits of integration. So we'll have to find them. All right, so to find the intersections of two polar curves, all you do is set them equal. That kind of seems like a no-brainer. But you have to remember, though, polar curves are being traced out based on the angle, theta. And depending on the curve, they may trace out that curve at different speeds. So one function may be going around the circle really, really fast, but another one may be going around your limacon and may be going slower. So even though they intersect, they may not be at that intersection at the same time. So when you're putting these in the calculator, you're going to see this. So I don't know that I can kind of draw one or not for you, but because I can't draw two curves at one time. But if I had something going on here with a circle, and then I had another picture maybe of a limacon, all right, that has a little circle in it. All right, what's going to happen here is this limacon, when it's tracing out, it's going to start here at 0, and it's going to go around this way, and then come to the loop, and then come back to the start. The circle is starting, the circle is starting here at this right-hand side, and it's going around just like this. So we do see an obvious intersection point right here, okay? The thing is, they may not both be at this intersection point at the same time. So for instance, going around this limacon, we may be, let's see, where would we be? Let's see, I would be here, here, and here. So that would be pi. And then this is pi all the way around. So just pi over 2, yeah, so it's probably not going to be there at the same time, because if I'm going 0 to pi over 2, I'm up here. But the circle 0 to pi over 2 gets back to the origin that fast. So I doubt they would be at the same place. And you could put them in a circle. If I had equations for you, you could put them in your calculator. But as they both start right here on the right, and then the point's going to travel around the curve. So the circle may be already over here by the time my limacon gets to here. So they're not going to pass necessarily through this intersection point. I hope I'm making sense. They're not going to pass through this intersection point at the same time, but they still have an intersection point there, is what I'm trying to say. So they don't trace along their curves at the same speed. So therefore, they may intersect the point, but not simultaneously. They may not get there at the same time. Thus, to find all the points of intersection of two polar curves, it's easier to draw the picture of the curves or use a graphing calculator and see how they interact with one another as they're being drawn. So we're going to be doing some heavy calculator stuff on this section. Now, if we were doing it by hand, you'd have to know these identities. All right, cosine squared theta is 1/2 of the quantity 1 plus cosine 2 theta, and then the sine squared is exactly the same, just with a minus sign. So they're not hard to memorize because sine just has a minus sign. That's the only difference. So if we were going to do these by hand, we would have to trade out cosine squared theta for these identities in order to make the integration a lot easier. All right, if you wanted to practice that. But if I want us to, I'll make us. But if not, we will just math not everything. So let's just introduce area here to begin with. All right, so find the area, and the picture's already drawn, so we don't have to save our time with putting in the calculator and figuring out stuff. So we want the area of one loop of this 4-leafed rose. So this starts here at 0, and by pi over 4, it already goes back to the origin, and then by pi over 2, it comes to here. So I'm going to draw it like your calculator would draw it. So 0 to pi over 4, and then to pi over 2, all right? And then it would keep on going. So this is how this gets mapped out. All right? So this part of it is really quick here. That's part of it right there. And then it goes to here, and then it goes to here, and then it goes to here. So that's kind of the 4 quadrants. So this is quadrant 1. Let me start over here and show you again. So if you type this equation into the calculator, you'll see it. All right, starting here, quadrant 1, 0 to pi over 2. That's quadrant 1. And then quadrant 2 is pi over 2 to pi. So this is pi over 2 to pi. Pi over 2 to pi goes here. So here's quadrant 2. So at pi, we end up right here. But at pi over 2, we're down here at the bottom. So this starts here and goes here. Then from pi over 2 to pi, it goes to here. Then when we're doing pi over 2 to 3 pi over 2, it maps around to here. So when we're actually down here at 3 pi over 2, the function graphs up here at the top. And then from 3 pi over 2 to 2 pi, it graphs this other little piece right here. So that's how this little rose maps out, okay, when it's going 0 to 2 pi. So to get this one little flower here, I'm 0 to pi over 4. Pi over 2 takes me way down here. So 0 to pi over 4 is this upper piece. So to get this bottom piece, it's just easier to think of this as going 0 to negative pi over 4. All right, going backwards. So to get this one petal of this 4-leafed rose, we need to integrate from negative pi over 4 to positive pi over 4. So our area, following the formula, we're going to integrate from negative pi over 4 to positive pi over 4. And the formula is 1/2 r squared d theta. 1/2 r squared d theta. So this is our r. So cosine 2 theta squared. And so then you can just math 9 that, and you're going to get an answer of 0.393. Okay, 0.393. Now, so you might be thinking, okay, but if we did it by hand, okay, I know nobody wants to do it by hand. Do you want to do it by hand? All right, well, let me give you a little hint on what would happen if we did it by hand, just to kind of preface this. I gave you the little trade out that cosine squared equaled 1/2 1 plus cosine 2 theta. All right, that cosine squared of theta equaled 1/2 of the quantity 1 plus cosine 2 theta. Now, you'll notice in this problem, we're going to end up with a cosine squared 2 theta. Well, that's easy to remedy. All we got to do is make this a 2 theta, and this over here becomes a 4 theta. All right, so we end up with cosine squared 2 theta, 1/2 1 plus cosine 4 theta. So that's all you do. You put in place of this theta, put a 2 theta. In place of this theta, put a 2 theta. So that's going to make that 4 theta. So if I had a problem here that was cosine 3 theta, then I would put a 3 theta in here, and put a 3 theta in here would make 6 thetas. So you just substitute in, and then it works out just perfect. And so you're going to replace the cosine squared, because this is going to be in squared, you replace the cosine squared with this expression. And then we can integrate that expression by hand and get the answer. All right, this is much easier to integrate than the squared, because you're going to replace this and just multiply by 1/2. So that's going to be a 4th times this, and then you can integrate that easy. Okay, you know the antiderivative of cosine 4 theta. Okay, all right, so the answer was 0.393. Let's go to number 2. Find the area of the region. So now this is an example of where it's a region between two. So here's where, all right, I want to show you that we've got a circle. So this red one is a circle kind of outlined in red there. And then in here, we have a cardioid, okay, because it doesn't have the loop. So that's a cardioid. So we want the area of the region that lies inside the red circle, but we want to be outside of the cardioid. So on the outside of the cardioid, but inside the circle. So that's this red shaded crescent moon part right here. So we want that area. Okay. So in order to find the intersection points, we would set these equal to each other and solve and find their intersection points. Okay. That's already been done for us. They intersect at pi over 6 and 5 pi over 6. So right now, I'm giving you a little bit of a break from having to do that right now. Just getting you to do the area. All right. So our area is equal to, we're going to go from pi over 6 to 5 pi over 6. and it's 1/2. And since we are having an area between two curves, I'm going to write it in here first. It's big R squared minus little r squared d theta, just like when we had like washers. All right, so we've got to figure out who is our closest curve and who is our furthest away curve. And that's what we're going to put in here. All right, so I think about this again as a little lighthouse, sweeping out and going, moving from left to right and sweeping out the ray from the pole, okay? So as it does so, the furthest away curve is out here. So that's my big R out here. So that's going to be the circle, and it's the circle all the time. So the circle is the big R, so that's going to be 3 sine theta squared. So I'm going to go ahead and square that and make it 9 sine squared theta. Minus, and then that leaves the cardioid to be the inside little r function, right? So since that's a quantity, I'm going to go ahead and just do 1 plus sine theta quantity squared, and then d theta. All right, so there is my integral, and we can just math 9 that, and when you math 9 that, you should get 3.142. 3.142. So that would be the area of this red crescent shape, 3.142. So that's the area inside the circle, but outside the cardioid. All right, so the last thing I want to talk about, because I'm just opening up here the area and just talking about how to find area of a polar curve and then area between two polar curves, and it's going to get a little bit harder as we go along and do a few more activities with this. It says find all points of intersection of the curve. So let's practice. What if they give us a problem and they want us to find the area inside one and outside the other or whatever, but they didn't give us the intersection points? Okay, so what we need to do is we have got to solve those intersection points ourselves in order to do the integrals. So here's a practice problem on finding intersection points. So I've already graphed the first one here. This r equals cosine 2 theta. That's a rose with 4 petals. Remember, if this number's even, you double it. So this is a 4-petal rose. And then r equals 1/2 is a circle, and it's only halfway out. So instead of being 1 unit out, it's only halfway out. All right. Now, this, I want to, let's see. I want to show you how to, like I did before with the mapping around. So this starts here, and when it maps around, it goes around here, remember, goes down here first, and then it comes back over to here, and then it comes back up to the top up here at 3 pi over 2, and then it goes over here to 2 pi. So when you type this in the graphing calculator, you're going to see that it swings around like that. That's how it maps around. All right, so now let's see. So I just drew this picture nice and big for you so you could see what you got. So we want to find the area, well, no, we're finding the intersection between of the two graphs. So as I explained earlier with finding intersections, you want to just set them equal. So because r equals this and r equals this, we want to know when the r length from the pole is the same. If they both have the same r length from the pole, whether they're there at the same time or not, because remember this circle is going to be going around here really fast while this guy's looping around this way. So they may not hit their intersection points at the same time, but the distance from the pole will be the same. So we want to set cosine 2 theta equal to 1/2, solve. So we need to think on the unit circle, where is the cosine 1/2? So I'm just thinking on the unit circle, cosine 1/2, that's my x-coordinate. So over 1/2 and up, over 1/2 and down. So what are these values here? Well, this is pi over 3, and this one down here is going to be 300. So that's 5 pi over 3. Because this is 60 degrees up, 60 degrees back, so that's 300. So 5 times 60 is 300. So that's pi over 3, 5 pi over 3. So that means this answer here, 2 theta, has to equal pi over 3 and 5 pi over 3. All right, so then when I divide by 2, that's going to give me pi over 6 and 5 pi over 6. Now, I want you to see here something's happening. This actually has 8 points of intersection. All right, there are 2 here, there are 2 here, there are 2 here, and there are 2 here. There are 8, look how pretty that is. All right, there are 8 points of intersection. Notice I've only found 2. When I divided by 2, notice pi over 3 to 5 pi over 3, that was within 2 pi because this is 300. But I divided by 2, so now I'm only going to 150. So I probably need 2 more points. So how do I find my other 2 values? Well, if I'm at pi over 6, or pi over 3, excuse me. If I'm at pi over 3, how do I get to pi over 3 again? I'm going to go around 2 pi. All right. So I need to add 2 pi to this to find the next answer where I hit pi over 3. So how do you add 2 pi? Well, 2 pi in thirds is 6 pi. 2 pi in fourths is 8 pi over 4. All you're doing is doubling your denominator. So anytime you want to add 2 pi to a fraction, just add double the denominator to the top. So I'm going to add 6 to the top. That'll be 7 pi over 3. Add 6 to the top will be 11 pi over 3. And now to get the answers, divide by 2. So divide by 2 will be 7 pi over 6 and 11 pi over 6. Now, notice I now got, that's 210. So that's one of these points. And this is 11 pi over 6. That's 330. So that's one of these points. Okay? So now I have 4 points. Now, I told you there were 8. If I just add 2 pi again, if I add 2 pi to this again, so if I added 6 to this, that'd be 13 pi over 6. But 13 pi over 6 is the same thing as pi over 6. So adding 2 pi again is not going to help me, because if I go up here and if I add 6 to this and make 13 pi over 6, pi over 3, I'm back to pi over 3 again. So if I try to do that trick again, I'm going to get these same 4 answers again. So that's not going to help me. So what you need to do is think about this circle. Is there another way to represent this circle that has a radius of a half? All right. Well, a radius of a half, I can think of this as also negative 1/2. Because can't you go out the positive way, but also go the negative way? So if I am at 0 and I do negative 1/2, I'm going to be on this side of the circle and positive 1/2 on this side. So another way you can represent the equation of the same circle is to say that the radius is negative 1/2, which just flips you backwards. All right, so that means I'm going to can do this again, but do negative 1/2. Cosine of 2 theta equals negative 1/2. So now I'm going to do the same thing. So I need to think about on my unit circle where my cosine is negative 1/2. So negative 1/2 up here, negative 1/2 down here. So I'm thinking where this is 2 pi over 3, because that's going to be 120. And down here, this is 4 pi over 3, because that's going to be 240 for these 2 answers. Okay? So now I've got 2 theta equals, my choices are 2 pi over 3 and 4 pi over 3. And again, that's only 2 answers, so I need to add 6 to it. So add 6 will be 8 pi over 3. 6 to this will be 10 pi over 3. But that's what 2 theta equals. I want theta, so divide by 2. So that's going to be 2 pi over 6. 4 pi, and I just always multiply the denominator by 2, 6. 8 pi over 6. 10 pi over 6. So there's my other 4 answers. And I left them in 6 because you could reduce these to pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. But I left them in 6 so that you can see a pattern here going on. All right. This is pi over 6, and this is 2 pi over 6. 5 pi over 6, and 4 pi over 6. and then 7 power 6 and 8 power 6, 11 power 6 with 10 power 6. So we've got 1 and 2, 4 and 5, 7 and 8, 10 and 11 power 6. All right, so remember this thing maps around this way, right? All right, so when we come to power 6, we're here. When we come to 2 power 6, we're down here. When we come to 4 power 6, we're over here. 5 power 6. And then when we come to 7 power 6, we're here. 8 power 6, we're here. Swing around to here will be 10 power 6, and then 11 power 6, and then back to 2 pi. So remember, this thing twirls around like this. So 1 and 2 power 6, you would think at first that this is 1 power 6 and this is 2 power 6, but that's not true. 1 power 6 is here, and the 2 power 6 is down here. So 1 power 6, 2 power 6, 4 and 5, 7 and 8, and then 10 and 11. All right. So you just got to think about how these are mapped out in a circle instead of just thinking it's just straight around. Now the circle's going like this, but they just don't intersect those points at the same time, but they do have those intersection values. So their R value, their distance from the pole, is the same at those 8 values, is what the thing is, which in this case would be a half, because that's how far the circle is from the pole. So that means on the rows at these 8 values, the distance from the pole is a half, okay? Or negative half going the other direction, right? But a distance of a half. All right, so that's how you do intersection points. That's probably a hard one. I gave you a hard one to do that you had extra points to find. So that's a hard one. Most of the time when you just set them equal, the answers pop out. But that's why having a graph is helpful. If you have the graph there, then you can see how many intersection points you should have, and then you're able to manipulate and figure out how to find them. All right. So we are just starting area. There's several things I still got to talk about, because we want to talk about finding area inside loops and outside of loops. And so there's a little bit more to talk about with things like that. So this just introduces area of polar equations to you and how to find intersections. So I believe your assignment, well, this is length of a curve. We're not going to cover arc length, but I just wanted to show you, if you're curious, how do you find the length of the arc? It looks very similar to the length on the parametric equations, but for polar curves, it's the square root of r squared plus dr d theta squared. So this is the equation for finding the length of the arc on a polar curve, just in case you were curious and wanted to know. But again, we're not going to do that. So here's your assignment, is 668, 1 to 35 odd. There's a lot of different ones on here that we're going to need to talk about, like finding areas inside loops and things like that, and what happens when you're looping around and tracing out these things. So this is going to take us more than one day to do. So you can try a few of those problems, and we'll talk about this a little bit more when we're in our Zoom.